Chapter 9, Exponents and Logarithms. So before we begin, I just want to show you a quick percentage shortcut. Okay, so for example, let's say you want to add 5% of a number x to the number x. Well, basically, you start with 100% of x, and you want to add 5% of x. So in terms of a decimal, if you want to add the percentages, you could say it equals 105%. Okay, but in terms of decimals, if you move the decimal over two places, that's 1.00. And if you move this decimal over two places and add a 0, it's going to be 0.05. So that equals 1.05. So in order to add 5% of x, you just multiply x times 1.05. And that's going to be 1.05x. And that basically just adds 5% of x to x. All right, that's a shortcut. So let's say for another simple example, you want to invest $100 and add 5% per year. There's actually two ways we can do this. And that's going to be simple versus compound. All right, so let's look at each case. We're investing $100 initially and adding 5% per year. Simple versus compound. All right, so when you do simple interest, you're going to add the percentage of the initial amount each year. And since we're only doing a percentage of the initial amount each year, you're going to be adding the same number each year. As a result, since you're adding the same number each time, the graph is going to be linear. So let's take a look. All right, so this is the year. We'll start at year 0, 1, 2, 3. In year 0, the initial amount is $100. Okay, and then the next year we take $100 and we add 5% of 100. And that equals 105. And the next year, we start with 105. And we add 5% of 100. And that's 110. And the next year, we start with 110. And add 5% of 100. And that's 115. Okay, so notice each year we're adding $5. All right, we started with 100, so it goes up by the same amount each time. Now, if you were to draw a graph of this, all right, we had the year for the x's and the amount for the y's. Okay, the x-axis would be the year and the y-axis would be the amount. All right, you started with $100 at year 0 and it just goes up by 5 each year. So it's a straight line, that's linear. Now, for the compound interest, you're adding a percentage of the new amount each year. As a result, since you're adding a percentage of the new amount each year, you're multiplying by the same number each year. Remember, for the simple interest we were adding, now we're multiplying by the same number each year. And as a result, the graph is going to be exponential. And instead of linear, it's going to be exponential. It's going to be a curve. So again, let's do the year and the amount. Okay, we're going to start with year 0. And then we're going to go up to year 3. In year 0, we start with $100. Now, we said at the beginning of this lesson, in order to add 5%, you can multiply by 1.05. So, in the first year, you're going to take the initial amount of $100 and add 5% by multiplying by 1.05. In year 2, you're going to take whatever you got here, okay? So that's going to be 100 times 1.05, and you're going to add 5% to this new amount. How do we do that? Well, we just take this new amount and multiply it by 1.05. Okay, and again, we're going to take whatever you got here. So that's going to be 100 times 1.05 times 1.05, whatever that number is. You're going to take that amount and add 5% to that new amount by multiplying once again by 1.05. Okay, so basically, this first one is 100 times 1.05 to the power of 0. Okay, this is just 1. This equals 100 times 1.05 to the power of 1. This equals 100 times 1.05 to the power of 2. All right, and the last one equals 100 times 1.05 to the power of 3. Okay, so notice each year it's going to be times 1.05 each year. All right, and as a result, if you do year on the x-axis and the amount on the y, okay, the year is on the x-axis and the amount is on the y. We started right here at $100, but you're adding 5% to a bigger amount each time, so it's going to add a bigger amount each year because the money keeps growing and you're adding 5% to that new amount each time. So this graph is going to be exponential. All right, so that is the difference between simple and compound interest. All right, so we have a formula here. If P dollars is invested, T is the number of years, and R is the interest rate. All right, so we're going to be using those, and A dollars is basically the amount. We're going to be using this formula here. All right, P is the number of dollars invested, T is the years, R is the interest rate, and this right here is the formula. A equals P times 1 plus R to the power of T. All right, so A is the amount or the accumulation, how much money you have in the account. P is the initial investment. All right, it's called P because it's basically the principal amount. All right, so we'll say initial amount. R is the interest rate. And T is the time. All right, so that is the formula we'll be using at first for compound interest. All right, so first example, they want us to find the compound amount. We are investing $5,000 after 3 years, earning 6% interest compounded annually. All right, so let's see. The $5,000 is the initial amount, so that's P. The 3 years is the amount of time. The 6% is the interest rate, but we need to convert that 6 to a decimal. So if you take a number 6 and you move the decimal to the left 2 places, that's 0.06. All right, and compounded annually, that just means per year. All right, so using our formula, we said A equals the principal amount P times 1 plus R to the power of T. All right, the principal amount is $5,000 times 1 plus R is 0.06 to the power of T. T is 3 years. All right, you can enter it in a calculator like that, or you can just clean it up a little bit. 1 plus 0.06 to the 3rd power. All right, the units were in dollars, and I get 5,955.08. I did not have to round in this case, but normally when dealing with money, dollars, you round off to the nearest 100th or 2 decimals. All right, example number 2, we're investing $10,000 after 8 years at 7 1/4% interest compounded annually. So see if you can get that one started, please. All right, $10,000 is the initial amount, that's P. 8 years is the time. 7 1/4 is the interest rate. However, if you take 7 1/4, that's the same as 7.25, but you need to move that decimal over 2 places and add a 0. So that's going to be 0.0725. So the interest rate R is actually 0.0725. All right, we said compounded annually means per year. So, using our formula, A equals P times 1 plus R to the power of T. P is the initial amount, that was $10,000, times 1 plus R, and R is 0.0725. To the power of T, that is 8 years. All right, you can enter it in the calculator just like that. But if you want to clean it up, that's going to be 1.0725 to the 8th power. All right, and this time I did have to round off. I get 17,505 and 66 cents. Okay, on my calculator, I actually got 0.656, and it kept going. So if you look at the 3rd decimal, if it's 5 or more, you round it up. So the 0.65 became 0.66. All right, so I'll write this formula in the notes. But many investments pay more often than once a year. Okay, so instead of using the annual interest rate, we use the interest rate per period. So, if there are n compounding periods per year, the interest rate per period is R divided by n, and the total number of periods is n times t. All right, maybe I should highlight that in a different color. Let me fix that. All right, N is the number of compounding periods per year. Interest rate per period is R divided by N. Okay, and the total number of periods is N times T. So here is the new formula. And instead of 1 plus R, it's 1 plus R over N to the power of NT. Let me write this in the notes. So the new formula is A equals P times 1 plus R over N to the power of NT. All right, all the other letters are the same, but N is the number of periods per unit of time. All right, usually that's in years. So N would be the number of periods per year, but it could be slightly different. Okay, and since R is the interest rate, R divided by N is going to be the interest rate per period. All right, example 1, find the compound amount. All right, so here we are doing $5,000 after 3 years, 6% interest. All right, compounded semi-annually. Semi-annually means 2 times per year. And monthly, of course, that means 12 times per year. So the principal amount is the initial amount invested. So clearly the P is $5,000. The time T is the number of years. That's 3. 6% we said was annual interest. We said was R, and 6% we said was 0.06. Okay, and if something occurs twice per year, the number of periods N equals 2. If something occurs monthly or 12 times per year, the number of periods N is going to equal 12. All right, so let's see for part A, we're going to use our formula A equals P times 1 plus R divided by N to the power of N times T. All right, the initial amount P is $5,000. That's going to be 1 plus the interest rate R, which is 0.06. And the number of times per year is 2. To the power of N, which in this case is 2, times T, which is 3. All right. Now, you can enter it on the calculator just like this. You have to use parentheses around your exponent on most calculators, or if you want to clean this up, it's going to be 5,000 and 0.06 divided by 2 is 0.03, and 1 plus that is going to be 1.03. And of course, 2 times 3 is 6. All right, so you can clean it up or you can enter it just like that. Round off to 2 decimal places. All right, and I get 5,970 and 26 cents rounded off. Okay, part B, same formula. The principal amount invested was $5,000. 1 plus R we said was 0.06 for the R. And in this case, it's monthly, so N equals 12. We're dividing by 12. Okay, N equals 12 right here. And the number of years T was 3 years. So the exponent is actually 12 times 3. Okay, you can stop right there. and go to the calculator. If you want to clean it up, this is 0.005, so 1 plus that is going to be 1.005. All right, that's going to be 1.005. And of course, 12 times 3 is 36. Okay, I'm going to use the squiggly lines instead of the equal sign because I'm really rounding off here. And I get 5,983.40. Okay, now notice the same interest rate gave us more money in Part B. And that's because it was compounded more often. It was compounded 12 times per year instead of 2 times per year. So more compounding means a little more money, even though the interest rate was the same. All right, please try the second example using $10,000, 8 years, 7 1/4% interest, compounded weekly. Okay, I'll give you a hint for the compounded weekly. N equals 52, since there's 52 weeks a year. Use this formula, please try it. All right, 10 grand is the principal amount, P. 8 years is T, the time. 7 1/4 interest, 7 1/4 is the same as 7.25, all right, and if you move the decimal over 2 places, that's 0.0725. And we said N equals 52. All right, just in case you couldn't get the 725 here, if I started with 7.25, that's the same as 7 1/4, which was given in the problem. If you move the decimal 2 places to the left and add a 0, that's 0.0725. So that's how I got it. All right. P, 10 grand, $10,000 invested, times 1 plus R, 0.0725, divided by N, the number of periods, which is 52. Because there's 52 weeks in a year. It's compounded weekly. Okay, N is 52. And the time T is 8 years. So the exponent is 52 times 8. Okay, I'm not even going to simplify this one. I'm going to go right to the calculator. Just be careful when you do your exponent. You may have to do the exponent in parentheses. But please make sure you can do this on your calculator, so please try it and get the correct answer. All right, I get 17,853 and 17 cents. Continuing with Chapter 9, we are moving on to continuous compounding. So you want to imagine compounding more and more frequently. And remember in this formula here, that N is the number of periods, okay? And that's in this formula right here for compound interest. All right, so we covered this the other day. And what you want to imagine here is compounding more and more frequently. So if it were quarterly, and N is the number of periods, quarterly is 4 times a year. And if it were weekly, there's 52 weeks in a year. That's 52 times per year. Daily would be 365 times per year. And if you kept going more and more frequently, eventually N would go to infinity. Okay, and that is what continuous compounding is, when N equals infinity. Imagine every second, every millisecond, and so on and so forth. All right, so if N is infinity, this formula here becomes A equals P times E to the power of RT. All right, that E is not a variable. E is a number. It's approximately equal to 2.018, and you should be able to find it on your calculator. Okay, so this formula right here is for continuous compounding. All right, so first example, they want us to find a compound amount of $5,000 after 8 years, earning 12% annual interest and compounded continuously. All right, so we said that for the continuous compounding, A equals PE to the power of RT. This is actually easy to remember. A equals PERT. Okay, so the initial amount invested is the principal. That's 5,000. The time T in years equals 8 years. And the interest rate R, you move the decimal over 2 places, and that's going to be 0.12. All right, so pretty simple. The P is $5,000. And that is going to be times E to the power of R, which is 0.12, times T, which is 8 years. All right, wrote that a little sloppy. All right, so I'm going to do this on the calculator. The exponent here is actually 0.12 times 8. So make sure you can enter this on the calculator. All right, you have to find the E button. So I'm going to do 5,000 times, and I have E on my calculator, to the power of, parentheses, 0.12 times 8, close parentheses. And I get 13,058.48. 13,058.48. Okay, I rounded to 2 decimals because we are dealing with money, so round it to the nearest cent. Let me see if I can do this on the screen. Okay, 5,000 times E to the power of, parentheses, wait a minute, let me fix this. Okay, 5,000 times E, X to the Y is your exponent button, and the exponent right here, I'm going to use parentheses, 0.12 times 8, close parentheses, so that whole expression is the exponent on E. And I hit equals 13,058.48. All right, so it checks out. All right, I'm going to write this in the notes, but for population growth, it's basically the same formula. N of T equals NO times E to the power of RT. I'm going to write notes on that. That's if it's increasing, and if it's decreasing, the exponent just becomes negative. All right. All right, so the population growth is really the same formula as A equals PERT. Okay, but they call it N of T equals N sub 0 times E to the power of RT. So what they mean by N sub 0 that is just the amount at time 0. Okay, and R is the growth rate. And T, of course, is the time. All right, and for the time and the growth rate, the units must match. So it's basically the same thing. A equals PERT, it's just using different letters. Okay, so that's for population growth. And for decay, it's the same thing except the exponent is negative. So n of t is going to equal n sub 0 times e to the negative rt. And of course, in this case, r is the rate of decay. All right, so in other words, you could say that it's losing 10% per year or something along those lines. All right, example 1. The population of a city is estimating to be growing at a rate of 10% per year. In 2000, its population was 160,000. Estimate its population in the year 2005. Okay. Notice it doesn't say how often it's compounded, and that is because when you are dealing with population growth, that is continuous. All right, when you're dealing with population, that's continuous. So it's still A equals PERT, but we write it as n of t equals n sub 0 to the power of n sub 0 times e to the power of rt. All right, so we said n sub 0 is the initial amount, and we can see in the problem, in the year 2000, it was 160,000. All right, so the initial amount, n sub 0, is 160,000. The growth rate is 10%, so R, as a decimal, 10% is 0.1 or 0.10. Okay, you don't need to include the 0, but I like to do that to show that it came from the number 10. All right, and the time, it went from 2000 to 2005. Okay, so how many years is that? Well, that's just 5 years. All right, we started in the year 2000, and we want to find the population in 2005. So I don't need to show you 2005 minus 2000, that's just 5. All right, once you have all the numbers, it is pretty simple. N sub 0 is 160,000. I'll write it underneath. N sub 0 is 160,000. And that is times E to the power of R times T. All right, R we said was 0.10, so this is an exponent now on the E. That's 0.10, and that is times, that is times T, which we said was 5. All right, pretty simple. N sub 0 is the initial amount, R is the rate, and T, let me clean this up here. T was just the number of years. All right, so I hope you can read this. This exponent is 0.10. I use parentheses instead of a dot because I don't want you to get confused between the decimal point and the times symbol. This here is times, this here is a decimal. These are multiplied. All right, and make sure the units match on the rate and the time. Let's make sure the rate was 10% per year. Okay, and the population was measured in years as well. Okay, so I'm going to do this on the calculator. Make sure you can as well on your calculator. And I'm probably going to have to round off, so I'll use the squiggly lines. And I get 263,795. Okay, and the decimal kept going. But general for population, you round off to the nearest whole number because you generally don't have a half of a person, okay? So you round off to the nearest whole number when dealing with population. All right, second example. A county is losing population at a rate of 0.7% per year. Okay, if the population in 2001 is 1 million, what is it expected to be in the year 2008? All right, so since we're losing population, we are going to use the decay formula. All right, and the interest rate, or the rate of decay, if you start with 0.7, all right, if you start with 0.7, because it's 0.7%, and you move that 2 places to the left, and you add in the zeros, that's going to be 0.007. So 0.7% is equivalent to 0.007. All right. Now, let's see. The population in 2001 is 1 million. So that is our initial amount, n sub 0. And t is from 2008 to 2001. So you just subtract 2008 minus 2001, and of course t equals 7. All right, so now we're in business. We're going to use the 1 for decay. All right, so it's still A equals PERT, but instead we say N of T equals NO times e to the power of RT. But since it's a decay, now it's going to be to the power of negative RT. All right, so it's still basically A equals PERT, but the exponent is now negative. All right, NO is the initial amount, that's 1 million. And that is going to be times e to the power of negative r, so it's negative 0.007. And that is times t, and that's going to be 7 years. All right, this whole thing right here is the exponent. Make sure the units match. This right here says 0.7% per year, and the population is also measured in years, so we're in business. All right, so I'm going to do this on the calculator. Make sure you can as well. And rounding off to the nearest person, I get 952,181. Okay, does the answer make sense? Well, we started with 1 million. We started with 1 million, and we were decaying at a rate of 0.7% per year. So yes, after 7 years, you would think it would be a little bit less than 1 million. All right, this is example 3. In an experiment, a culture of bacteria grew at a rate of 35% per hour. And it says, if 1,000 bacteria were present at 10, how many were present at 10:45? All right, so it says that the bacteria grew. And remember, when we're dealing with population, we are dealing with continuous compounding. All right, so it is continuous, I think I spelled that wrong, continuous growth. All right, so we are using A equals PERT, but we write it as N of T, and that equals NO times e to the power of RT. Now we have a little issue here because I'm thinking the units do not match. So let's see what we can do to solve that one. The starting point at time 0, that's n of 0, is 1,000. All right. The rate is 35%, so R is going to equal 0.35. And okay, the rate is per hour. So we have to determine how many hours it is from 10 o'clock to 10:45. Let's see. If we end at 10:45 and we started at 10, obviously that's 45 minutes. But we need it in terms of hours. Okay, so how many minutes in an hour? Well, if you do 45 divided by 60, and then reduce 45 divided by 15 is 3, and 60 divided by 15 is 4. So 45 minutes is the same as 3/4 hours. Okay. Now, did we need to reduce? Not necessarily. Okay. We can let the calculator do the work and let t equal 45 over 60. But the easiest thing to do is convert that fraction to a decimal. Okay, so t is just going to be 0.75 because that's the same as 3/4. Now, if this were a repeating decimal, I would not round it off, okay? I would leave it as a fraction in the problem. But in this case, it's not really much of a problem. It's not a problem at all because 0.75 is exactly the same as that fraction. Okay, anyhow, n sub 0, we said that was 1,000. Okay, so for n sub 0, it's 1,000. And that's going to be times e to the power of r, which is 0.35. And that is times t, and t is actually 0.75. All right, if you had a fraction here, that's fine. You just need to learn to do that on the calculator. Anyhow, I'm going to use my calculator. And rounding off, I get 1,300. All right, does the answer make sense? Well, sure it does, because it was supposed to grow at 35% per hour. So if we started at 1,000, we expect it to be more than 1,000. All right, for present value, that's how much you need to invest initially. So in order to write a formula for this, we just have to work backwards. Okay, so we said for compound interest, A equals P times 1 plus R over N to the power of N times T. All right, so the present value is really just P, how much you're investing initially. So if you want to solve for P, you can, okay? Solving for P is times this mess right here. If I wanted it to cancel, I would divide by 1 plus R over N to the power of NT on both sides. All right, I'm just doing algebra here. I'm dividing both sides by the same number. Okay, just simple algebra. We started with this right here. I divided both sides by this part in parentheses in order to isolate the P. So this divided by this cancels. Okay, and I have P equals this mess right here. Now, instead of having it in the denominator, I'm going to take this whole thing and shift it up. Remember, when we did negative exponents, if you have 1 divided by x, and x is to the first power, that's the same as x to the negative 1. If you take this whole denominator and shift it up, you change the plus minus sign on the exponent. So same thing here. If I take a and I move this whole thing up into the numerator, I just keep the same expression, 1 plus r over n, but the exponent is now negative nt. Okay, and that whole thing equals p. So that right there is your formula for present value. Do you need to remember this? No, because you can always plug it into the original and then just solve for p. Okay, so you don't even have to start with this. If you only knew this formula, plug in the numbers and solve for p. Either way, it's the same thing. All right, last one. Find the present value of 20 grand due in 8.5 years, earning 6% annual interest compounded monthly. All right, so we said the present value P is going to be A times 1 plus R over N to the power of negative NT. All right, so the present value, the 20 grand is the value now. That's the current value, so that is your amount A. 8.5 years is the time T. All right, so T is going to be 8.5. 6% annual interest, so R is 0.06. And it is compounded monthly. Remember, N is the number of periods. So if it's compounded monthly, N equals 12. All right, so now we're in business. A is 20,000. And that's going to be times 1 plus R, which is 0.06. Divided by N, which is 12, to the power of negative N, which again is 12, times T, which is 8.5 years. All right, so there you go. Now you should be able to do this on your calculator. If you need help, let me know. All right, and round it off to the nearest hundredth. I get 12,025. And 18 cents. Now, once again, as I said before, do you need this formula? No, not necessarily. Okay, if you only had this formula here, if you had A equals P times 1 plus R over N to the power of NT, you can still plug in, you can still do algebra from here, or you can just plug in the numbers. You plug in 20,000 for A. You plug in all the numbers here, and whatever you get for this, you just divide both sides by that amount. Okay, whatever is in parentheses to the power of NT, it would cancel here, and that would give you P. Whatever you got there would be your answer for P. So this is just a little bit of a shortcut on the formula. Okay, it still works even if you use the regular compound interest formula.